Swayam Prabha. Digital India. Educated India.
We left at a place where we said what are the structural properties of matching if it has to be popular, right. So, we said that if it has to be popular, then every F post is matched to an applicant who treats it as treats it as a rank 1 post, and if M is popular, then every applicant is matched to either its FA or SA, and we argued that it cannot be matched to somebody strictly between F and S, else it cannot be popular. In a very similar spirit, you should argue that it cannot be matched to somebody who is strictly worse than its S of A. Otherwise, you should be able to come up with 2 promotions at the cost of 1 demotion to show that there is a more popular matching. So, this is the flavor of the argument here. So, so is this the end of the discussion? I mean, does this immediately tell us an algorithm? So, this tells us how it looks like. Can we immediately tell what is the algorithm to compute a popular matching? If you know so much about the structure of a popular matching, what is an algorithm that you will propose? Yeah. See, we have some people participating. It will be very nice if many of you participate. I understand that, yeah, you have, yeah, not everybody can answer at every point, but please attempt to participate so that it becomes a little more interactive. I know it is the end of the day, but. Okay, somebody from this, yeah, you people have been a little silent, so. First pose. So, she suggests the following algorithm, or she says that look at the F pose, then add edges to that. That is what I will do. I will be constructing a bipartite graph, which is a reduced graph. I will cancel out all the F pose which do not appear as rank 1, and then look for S pose, right, which are the second choice pose. Then she seems to suggest that look at those and then cancel them out further and look for third pose. Now, does this theorem allow us to do that? So, okay, so I will assume that you have proved that it cannot be below its S pose, because that is also crucial to this. Suppose you believe this, because the argument is very similar, so let us skip it. But let us say that it has to be between F and S, then should you go beyond your S post? You can look for third pose, that is not incorrect, but will a popular matching be able to match an applicant along its third post? Yeah, so since you suggested, what do you think? Sorry? Yeah, so second came, right? Yeah, so there is a second choice. In fact, maybe there is also a third choice. Let's say there are posts remaining after your S post. Should you consider them? Yeah, second statement, yeah, sorry. Yeah, we have assumed that it is completely proved. I have not proved this part that P cannot lie here, but assume that this is true, and it is not difficult to see, because if somebody is matched to its a post which is lower than its S of A, you promote it to its S of A if its S of A is free. If its S of A is not free, then there is somebody who is matched to its S of A. That person cannot rank it as its first post, therefore it has its own first post, promote that person, and you get 2 promotions at the cost of 1 demotion. So therefore this statement is true, that is, and if a matching is popular, then it cannot match anybody to outside its F post or S post. So then should we look for third post? A third post is only going to be below the S post, right? So therefore if we use that H, then that matching cannot be popular. So therefore there is no point in using third post. So therefore we should restrict ourselves to a graph where we will have the applicants, and we will now use some color coding. We will say that there are these red edges which are, for every applicant there is a red edge, it goes to some post. This post is its F post, and then there are also these blue edges which go to their S post. Every applicant has an S post. We do not know how there may be several applicants who have the same S post, some applicants who have their unique last resort as their S post, but every applicant has a blue edge and a red edge incident on it. Once we have constructed this graph, what question should we ask? Yes, we have constructed this graph. We know that if M is popular, it must reside in this graph. But what matching should we ask for in this graph? So we did it manually for an example, right? You actually constructed a matching, and we did not, we would like to show that it is, we would like to prove that such a matching is popular, but what kind of matching did you construct? Not the exact matching, but what were the properties of the matching? Which this? But remember, okay, so what she is saying is she matched some applicant to its L of A. Is it allowed to match some applicant to its L of A? Yes or no? Yes, because L of A can be a S of A for somebody. Therefore, it's okay to match it to its L of A. As long as you match every F post, it is okay to match some applicants to their L of A, right? So now we will simply construct this graph and compute a maximum matching of this graph. So this graph we will call as the reduced graph G prime. So G is the original graph, G prime is a reduced graph which has only 2n edges, and we will just compute a maximum matching in G prime. Now the maximum matching may be I mean, we just subject it to a maximum matching algorithm. There are several matching algorithms which can compute a maximum matching, but they do not have any regard to what is an F post and what is an S post, because those algorithms just operate on the graph. Therefore, they will just compute a maximum matching. In particular, in our example, they may have computed a matching which matches A1 to L of A1 and A1 does not match A1 to P1, right? It's just a matching of size, the largest size. Therefore, it doesn't know that LA is something which is last resort and dummy and so on. We cannot tell that to that algorithm. So therefore, it will output a matching which is a maximum matching. Now we will look at the matching, one by one and ask, look at a post. If it is an F post, if it is not matched, there must be some applicant who would like to get matched to that post. Takes any arbitrary applicant in F of P and assign it to that. Change the matching locally and keep doing this. You are not changing the size of the matching. You are not changing, if an applicant was matched, it continues to remain matched. There are some posts which will change their status, right? But you will always have you can ensure by this property that every F post is matched to an A belonging to F of P, and every applicant is matched to F of A or S of A, right? So we can compute such a matching. But these are only the necessary conditions for a matching to be popular, right? Because we have said that if M is popular, then it must satisfy these conditions. We would like to also argue that if you compute a matching which satisfies these conditions, then it is popular, right? If we argue this, then we are done. Then we will be able to prove that that matching that you constructed is indeed a popular matching for that instance, without manually verifying all other matchings and comparing the popularity. Is that fine? Okay. So, so what are the steps? We compute a maximum matching in G prime and then ensure that every F post is matched. This is not difficult because you just examine every F post. If it is matched, not do anything with it. If it is not matched, take an arbitrary applicant in its F of P and match it to that by removing its matched partner. So you can keep doing this and ensure that every F post is matched. How long does this take? This takes as much as time required to compute a maximum matching in a graph, plus this time which is linear time in the size of the instance, because it takes order n time to look at the posts and do this post processing. So it takes time which is required to compute a maximum matching. If you have a graph G with n vertices and m edges, then a maximum matching can be computed in m square root of n time by a very well known algorithm which is called as Hopcroft-Karp. We will not go into that. So a maximum matching can be computed in this time. So what is the size of our instance? We have n vertices. How many edges do we have? We have only 2n edges. We do not have a very dense graph. So this n is actually 2n. In fact, it can be even refined because it is 2n1, where n1 is the number of applicants, n is the total number of vertices, but we will live with this, and therefore our algorithm runs in time which is order n square root n, right. This is the running time of our algorithm. In fact, this can be improved to a linear time algorithm, but for now we will just say that there is a polynomial time algorithm, assuming we prove the sufficiency, that is, if a matching satisfies these conditions, it is also popular, right. Okay. So we want to show the sufficiency, that is, if M satisfies the two conditions, I won't write them again, then M is popular. Okay, so suppose my algorithm outputs a matching M by doing those steps, that is, it computes a maximum matching in that reduced graph and it does a post processing of the post so that every F post is matched. I get a matching M, and suppose it is not, so it satisfies the two conditions, yet it is not popular, right. So if it is not popular, there must exist, so M is output by the algo and it satisfies the two conditions and satisfies two conditions. Yet M is not popular. So then there must exist an M prime which is more popular than M. Otherwise we cannot say that M is not popular. To say that some matching is not popular, there must exist some other matching which beats it in terms of the votes, right. So what do we know when we did this comparison of M versus M prime in terms of these applicants, right? A1, A2 up to AN, there were n applicants. What do we know when we constructed this voting table? if M prime is more popular than M? So the number of votes that M prime got is more than the number of votes that M got, right? That is why it is more popular than that. So in particular, there must exist an applicant AI who votes for M prime. If all applicants vote for M, there cannot be the case that the matching M prime wins. So this AI is some applicant which must have voted in the favor of M prime. So we ask, what did this matching M, the matching output by our algorithm which satisfies the conditions, where did it match AI? We do not know anything about M prime. M prime may look completely different from the conditions of the lemma, this statement, right? We do not know, we have no handle on M prime. So we look at this AI and ask, who is your, so we will call this matching the red, okay, red I have used, but so the green matching and this as the pink matching M prime, right? So there is a green, so should it be matched in the green matching? So AI should it be matched in the green matching? So go back and ask what were the conditions of this, that is every applicant is matched to either its FA or SA, right? Okay, so should it be matched? Yeah, green matching is M, which satisfies this condition. Should it be matched or not? Yeah, so you say yes, you seem to say no, right? Okay, so why do you say yes? Okay, so it seems to say that every applicant is matched either to its F of A or S of A. So therefore it must be matched. But why do you say no? Right, but I never said that it should not be a last resort, right? So it can be matched to a last resort. It may not be truly matched, but it is, at least in the dummy sense, it is matched. So it is matched, right? It may be matched to a last resort, but it is matched. So we have certainly a green edge. How that green edge looks like, we do not know. And it can be either F of A or S of A, because our matching always matches it to one of F of A or S of A. But what do we know about M prime? M prime also it is matched and it prefers M prime over M. That is, it prefers its pink partner over its green partner. Now if its green partner was F of A, could it prefer its pink partner? Remember that the pink partner must be different from the green partner, otherwise there is no preference, it may not have voted at all. So can this be F of A, the green partner? No. Therefore, the only choice that we have is its S of A, right? So this is the green partner which is S of A. We don't know what S of A is, it could be L of A, it could be a true post. Now what should we do? Okay, remember that we are not in the game now to show that there is a more popular matching, because M prime need not be popular, it may just be beating M. We do not claim anything about M prime, so we cannot play that trick. But what we can try to do is, if for every applicant AI that votes for M prime, just the way in the stable matchings we showed that there is another applicant AJ that votes for M, then these are unique applicants. For each AI I find another unique applicant that votes for M, then I am done, right? So I need to find some applicant who votes for M. So this is M. This is M prime of A. Yeah, so this is AI. Yeah, yeah, we want to do that. Yeah, we want to nullify the votes. We want to find one applicant who votes for M. Yes. Sorry, who? Mhm. Will vote for. Yeah, but who is that applicant? Right. Yeah, so let's ask where is f of AI? That's what you are saying, right? Okay, good. So there is some f of AI, right? Yeah, good. Huh. F of AI, let's call that some AJ. And this is a green edge actually, right? Is that correct? M of, so sorry, M of, uh, that is its M prime partner. We do not know what it is. Yeah. It is just better than S of A. Yeah, it need not be the first. We are not assuming M prime is popular. Yeah, but what can we say about, so let's look at the preference list of AI, right? So the AI has its own preference list. There is something which is, it could be F of AI, right? So why did I write AJ here? It's AI, right? M prime of AI, and this is also AI. So AI has a preference list and it has F of AI. We don't know what is M prime. This is S of AI, which is also its M of AI, right? It is its green partner. Okay. So whatever happens to this, whatever, wherever this M prime is, it is here, right? Before the, so it is somewhere in this range because it is better preferred than S of AI. So it could be F of AI or it could be anything better. Now what do we know about all these posts? I mean, this is its own F post, but what about a post which is sitting here? It is an F post for somebody, right? What does this, what happens to a green edge incident on this? This M prime of AI is some post, which is some P. Can it be left unmatched in the green matching? Because the green matching satisfies the two conditions. Therefore, there is a green edge incident on it, right? And that green partner of it is matched along, yeah, sorry, the green is different. The green partner of that is matched, is a rank 1 vertex, right? So, this AK treats it as a rank 1. Now, this AK, it's matched to its rank 1 in the green this thing. It cannot be matched to a green, it cannot be matched to a rank 1 in the pink matching, just because its rank 1 post is gone to some other applicant, right? Therefore, this AK vertex must give its vote to M over M prime, right? So, you are correct that we should try to find some applicant that is matched to its first post and it gives a vote, but it cannot be this, because these two people could be matched to the same, I mean, they could be matched in M and M prime in the same way. But we know that M prime of AI, which is equal to P, is matched differently in M and M prime, and therefore, this is a unique applicant AK which gives its vote for M versus M prime, and these two together compensate each other. Therefore, for every vote that M prime gains, you can just look at this path and get another applicant who must vote for M over M prime. And remember, this is a different, while it's a simple argument, it's a different argument from showing 2 promotions versus 1 demotion, right? Yeah, then the green matching cannot leave it unmatched. Yeah, so she's asking that can it be F of AI itself? It can be, and if there is no other applicant that treats it as a rank 1 post, then the green matching is not allowed to leave it unmatched. So therefore, it doesn't satisfy the conditions of the claim. Then we don't say anything about it, right? So therefore, now we know that this, if we output such a matching, then if the matching satisfies both the conditions of the theorem, then one, they were necessary, they are also sufficient. That is, if this is a matching that satisfies these conditions, then M is popular. So is this now the end of this discussion on, we know a complete characterization, or is there something that is remaining and which bothers you? Have we left something incomplete? Yeah, the size is a concern. That is, we showed that there are matchings of different sizes, and we can ask computing maximum cardinality popular matchings. That can be fairly easily done by saying that I would like to have least number of last resorts to be assigned to applicants. So that is one thing. Anything else that is remaining? What about this instance, the first instance that we saw? So what happens when we execute our algorithm on this? So we should also, our algorithm should also handle the case that it should be also able to say that the instance does not admit a popular matching, right? Because there are instances which do not admit a popular matching. So when will you say that the instance does not admit a popular matching? Yes. Yeah, maybe she's just answering and we'll come back to you. Yeah. A1 has P2, A1 has P1, P2, P3. This thing, you'll have to observe this, is it? Actually, you are right in some way, but how will you try to observe it in a large instance, and where will you try to observe it? I mean, this may be masked. For example, I can add some things in between so that this is not as apparent as it is here. So you are right in first 3. Only first post. If you have only first post and this is not there, then the instance does admit a popular matching. In fact, if you add this, then the instance stops admitting a popular matching. So we should make use of the theorem that we have. So we have stated a theorem that M is popular if and only if it satisfies the 2 conditions. We wrote it in 2 parts because we said that there is a necessity and there is sufficiency. So then what will happen to our algorithm? So maybe we should try to execute the algorithm on this. So we just do what the algorithm tells us. Everybody adds edges to F posts. This is A1, A2, A3. This is P1. Now what are S posts for everybody? For everybody it is P2, right? So we add these edges, P2. Now we compute a maximum matching in this graph. Any maximum matching must match only 2 applicants and it cannot match a third applicant. Now you cannot introduce a last resort and say that this last resort is your S of A, because that is not true. For A3, L of A3, there is an L of A3 sitting here because we pre-process the instance, but L of A3 is not even coming into picture. So its S of A is indeed P2, but you do not have enough posts between F and S to get matched. And if in this reduced graph where everybody has 2 edges, if you cannot find enough posts, or if the matching that you find is not a matching that is applicant complete, that is it matches all the applicants, that is it has size less than the size of the applicants, then you will say that the instance does not admit a popular matching, right? So I will just modify this algorithm. So ensure that every F post is matched, and then if, in fact you can do this immediately after computing the maximum matching, is if M matches all applicants, then instance admits a popular matching. Else instance does not admit a popular matching. Doesn't admit a popular matching. I would like to repeat this in this setting where we had this instance where there are n applicants, there is P1, there is only a single post. What is S of A? S of A1 is what is S of A1? P2. There is no P2, right? There is only P1 in the instance. There is a last resort, right? So S of A1 is L of A1, that is the last resort. S of A2 is L of A2, and so on. So the reduced graph, the original graph has n edges, the reduced graph has 2n edges, because everybody adds this dummy edge which we had called a pink edge, and this is, and now you can find an applicant complete matching which matches any one of them to its F post and everybody else to its S post, which is actually a dummy post. So it actually leaves it unmatched, but that doesn't mean that that matching is not popular, because our characterization does say that every applicant must be matched to either its F post or its S post. So as long as you find for everybody either an F or an S, you are happy. Any questions about this? Yes, you will have n plus 1 posts. Yeah, so we are not saying that the pose should get matched. It's not a perfect matching like we talked about in the stable matching setting where you had n and n. Right? Anything? Any questions? Yes. This example, right? Yeah, so what I am saying is, what does our algorithm tell us to do for this instance, right? So this instance we will actually convert the instance and write it with the pre-processing, right? A1, A2, A3 up to AN. Everybody has its, this is given to us, P1 is given as its top choice. This is all the instance that is there. Now we did a pre-processing step, that is we said that for everybody add L of AI, L of A3 here, L of AN, right. So everybody we add a unique last resort post, and now we ask what is F of A. F of A for everybody is P1. What is S of A? For each AI it is L of AI. Now you construct the reduced graph. The reduced graph has P1 for everybody, and then I think the green edges or the red, whatever, the green edges, and then there are these pink edges which are the S post edges. They are all dummy edges actually, but our algorithm allows us to do that. Our characterization says it's perfectly fine. So add those and then compute a maximum matching. The maximum matching does match everybody, at least in that graph. And then when we look at it, we ask, okay, even if everybody was matched to its dummy, we will take some applicant and match it to its P1 because we cannot afford to leave P1 unmatched, and then call that matching as popular because we have found an applicant complete matching. Contrast this with this instance where there is no popular matching because you do not have enough posts. While the original instance does have P3, but P3 does not come into picture, neither do LA1, LA2, LA3 come into picture. So what I want you to observe is that this addition of last resorts is not changing the answer from yes to no. It is really a convenience that thing that we have done so that S of A always exists.